So welcome back to the course of StatMech. So as we have discussed many things about statistical mechanics, now let us discuss more about statistical mechanics. I would like, if you mute your mic, it should be good. Then when you are having doubt, you can raise your hand. Yes, thank you. Thank you for your cooperation. So I will just give a short recap of what we have done and today what we are going to do. So in the initial time period we have discussed about the macro state microstate. That concept we have understand, macro state microstate, and we have we have done a brief introduction about the thermodynamics, about the laws of the thermodynamics, and what is entropy and how entropy is connected with the statistical mechanics, macro state microstate, phase space. We have discussed phase space in classical point of view, in quantum mechanical point of view. Then we have discussed about the classical statistics and quantum statistics. Basically, you can say in classical statistics we have discussed about the Maxwell-Boltzmann distribution, how we can find the occupation probability, and then we saw that quantum statistics, basically the distinguishable particles, indistinguishable particles like electrons, protons, bosons, mesons, or like all these particles, we need more complicated statistics, that is quantum statistics, and that also we have discussed. So now we are going to discuss the most important thing, a very important thing in statistical mechanics, that is what do you mean by density of states. Density of states, that is very much important to understand statistical mechanics. Density of states. So how we can define density of states, that is a very important point. Let us try to understand the density of states. Okay, so basically the Fermi-Dirac statistics, Fermi-Dirac statistics is applicable is applicable for is applicable for electrons, or like for muons, you can say. So we have discussed about the occupation probability. What is the occupation probability? It is f of e 1 by e to the power e minus ef by kbt plus 1. This is the occupation probability. You know probability is what? Uh, Whether chance is there or not there, that we have to find. Whether this state is occupied or this state is not occupied, that we are going to find using this particular formula or this particular relation. So before going to the occupation probability, we must know how many states are there, how many quantum states are possible. That we have to discuss. And for this, we will take the help of quantum mechanics. We will take the help of quantum mechanics. Okay. As you have done quantum mechanics, you know about the particle in a box problem. If you consider the particle in a box, the energy eigenvalue, we can write the energy eigenvalue. It is n square pi square h cot square divided by 2m a square. This is the energy eigenvalue. This is basically, if you want to find the 0-point energy, then you put n equal to 1, and this will give you E1 is equal to pi square h cot square divided by 2m a square. So this is the energy eigenvalue, and this is for what? This is for the 0-point energy, the minimum energy. Okay, we cannot take zero energy. Zero energy means no, they're not possible. We cannot take. Okay, if you read quantum mechanics, if you go to the rigid rotor, there you will see the energy eigenvalue will come 0, and we can give a proper explanation why zero energy is coming. But practically it is not possible, or in realistic case we cannot say zero energy. There is no such physical concept which gives idea about the zero energy. So no idea about zero energy. So for the ground state energy, we will put n equal to 1. So this will give E1 is equal to pi square h cot square divided by 2m a square. Okay, so this is basically for one dimension. Okay, this is for one dimension. We can extend this idea to 3 dimension, and this is basically, I can write for one dimension, E nx is equal to nx square pi square h cot square divided by 2ma square. If we go for 3 dimension, we will have E n y is equal to ny square pi square h cot square divided by 2ma square, and E n z is equal to E n z is equal to how much? Nz square pi square h cot square divided by 2ma square. You know that if you want to find the total energy, then you have to add all the energy. Add all the energy. This means you have to add these 3 equations to get the total energy. So what will be the total energy? We can discuss total energy. That is for 3 dimension. Total energy is basically what? Pi square h cot square divided by 2ma square. You can take common and you can write this as nx square ny square, and this will give me nz square. Okay, nx square plus ny square plus nz square, and this you can take as n square. You can take as n square. Okay, or you can take as capital N square. Let us take capital N square. Let us take capital N square. Okay, so this is capital N square is equal to nx square, ny square, and nz square. Okay, this is my capital N square. Is it clear? This is n capital N square is basically the yes, this is basically what capital N square is equal to nx square plus ny square plus nz square. Okay, so this is my energy, total energy. So I will get total energy as capital N square pi square h cot square divided by 2ma square. Okay, is it clear, Mister? This is my total energy. Okay, n square pi square h cot square divided by 2ma square. This is my total energy particle in a box. Okay, so this is when the length of the cube is a. If you consider a cube, basically the length, breadth, and height, they are going to remain same. In that particular case, you can take this formula, that is n square pi square h cot square divided by 2ma square. Okay, 1 minute. N square pi square h cot square. Okay, so n square pi square h cot square divided by how much? Yes, this is my total energy in particle in a 3-dimensional box. Okay, so you can find enx, eny, enz, and you can add all the component enx, eny, enz to get the total energy, and that will give you, that is n square pi square h cot square divided by 2ma square, where a is the length of the cube, where a is the length of the cube, where a is the length of the cube. A is the length of the cube. A is the length of the cube. Length of cube. Okay. If length is not same, okay, if a length is not same, in this case, the A is same along minus x, minus y, and minus z. All the direction, you will get the length. It is basically a cube. Cube means length, breadth, height, all are same. Okay. But in the case where this is not same, that is ax is not equal to ay is not equal to az. Are you getting my point? If ax equal to ay equal to az is equal to a, then you can write this is basically a square. If this is the case of cube, if you take a cube, then the length is a, breadth is a, the height is also a. So but in case of cuboid, if you take any other shape like cuboid, then the length is not equal to breadth is not equal to height. So in that particular case, how you can write the energy eigenvalue? Very simple. In this case, it will come a x square, this will come a y square, and this will come a z square, because they are not same now. In this case, cube, a x equal to a y equal to a z equal to a. So you can substitute a and you will get the energy eigenvalue. So you can find the total energy, that is total energy. Now you can write total energy is basically pi square h cot square, how much? H cot square divided by 2m, 2f, and you can write this as like nx square divided by ax square plus ny square divided by ay square and z square divided by az square. Are you getting my point, Mr.? And z square divided by a z square. So this is my energy, total energy. Okay, in this case, Ax equal to not equal to Ay is not equal to Az. When they are equal, you can write the formula like this. Basically, we are going to deal with this particular formula. We will find the total energy. Okay, so this capital N is basically equal to mx square, ny square, and z square. Okay, up to this, I think there is no doubt. So we can move. Is it fine for you? Okay, so okay, so let me clear all the drawings. Okay, okay, you can take the screenshot and we can clear this drawing. Okay, okay, yes. So now we can write the total energy. The total energy is basically how much? N square, and you got how much? Pi square. Okay, pi square h cot square divided by 2m a square. This is my total energy. Okay, and this n capital N square is basically nx square, ny square, and nz square. This is my capital N. Okay, so very important concept we need to understand, n square. Okay, see this nx basically it can go from 0 to any number. Sorry, not 0, it is basically starting from 1. If you take 0, the energy will become 0, and physically it is not possible. So nx can go from 1 to any number, but in practically this number is not infinite, because if you find the energy value, they are only finite. Okay, they are absolutely finite. So 1 to any number. So this ny also, it can go from what, 1 2 3 like that it can go, and z also it can go from 1 2 3 like that it can go. So this n capital N, it can go from 1 2 3 like that. As this nx goes from 1 2 3 any number, ny goes from 1 2 3 any number, and z go from 1 2 3 any number, and this n also go from 1 2 3 any number. So you can find the eigenvalue if you take c, if you take yes, if you take nx equal to 1. Okay, suppose let's say we will take n equal to 1, n equal to 1, n equal to 1, n equal to 1. If n equal to 1, then what is the total energy? The total energy is basically pi square h cot square divided by 2m a square. Okay, so what are the possible values of nx, ny, nz, so that we will get the total energy equal to pi square h cot square divided by 2m a square? What is the possible value? So that we have to understand. That we have to understand. So what are the possible values? This capital N square is basically what? Capital N square is basically nx square, ny square, and nz square. So if you take n equal to 1, then the energy is pi square h cot square divided by 2m square. And what are the possible values? So that we will get this one. We can find these possible values of nx, ny, and nz. So if you take nx equal to how much, ny equal to how much, and nz equal to how much, so that you will get this possible value 1. Okay, that we are very much interested. Okay, we are interested. You see, actually what we are doing, this nx equal to 1, ny equal to 1, nz equal to 1. This is actually n square. Okay, one mistake. So this is actually n square total energy. So total energy is basically what? Total energy is basically nx square, ny square, and nz square. Is how much? Pi square h cot square divided by 2m a square. So you can put this and you can find the 0 point energy, that is 3 pi square h cot square divided by 2m a square. This is my total energy. This is my 0 point energy, the minimum energy possessed by a system. This is nx, ny, nz. Both three are equal to how much? 1. Okay. So this much it is clear, I think. This is n equal to 1. N equal to basically the minimum energy is this much. If you take this capital N is basically, if you take capital N square is basically nx square, ny square, and nz square. So the total energy is basically how much? That is basically 3 pi square h square square divided by 2m a square. So this is the possible values of nx, ny and nz. Suppose if you are taking n equal to how much? N equal to uh, now what is nx, ny, nz? These are the possible values to give the total energy this much. Okay, now tell me, since this n square is nx square, ny square, nz square linear combination, so now what values of the energy we are going to get? This n square is basically nx square, ny square and nz square. So now we have taken nx 1 1 1. This is one combination. Another combination you can take this nx, you can take 1, ny you can take basically what? Ny you can basically take 2, and z is equal to you can take 1. This is one combination you can take. And for this combination, what is the n square value? It is basically 1 plus 4 plus 1. How much? 1 plus 4 plus 1. This is basically 6. So energy you will get 6 pi square h square square divided by what? 2m h square. This is the energy you are going to get. Or you can take nx equal to what? Nx equal to basically what? Nx is equal to basically you can take 2, or ny you can take a 1, or you can take basically this is 1. You can go for this combination also. For this combination also you will get the total energy same only. That is basically 6 pi square h square square divided by 2m square. Or if you take any other combination so that the total energy remains the same, this nx, ny and z combination will give you the degeneracy, because all are having the same energy, all correspond to the same energy. Whatever value you take for nx, ny and z does not matter, it will give you the same energy. That is called degeneracy. That is basically called degeneracy. I think some idea you have got. Okay, we can understand this degeneracy very well. That basically this m square, this n square is what? N square is basically nx square, ny square and nz square. So what are the possible values if you take n square is basically, what are the possible values of nx, ny, nz? If you take 1 1 1, this n square is basically what? 1 plus 1 plus 1 is basically 3. So n square is basically 3. So if you take 1 2 1 is another possible value, or 1 1 2, or 1 2 1, or 1 1 2, or like 2 1 1, like this. Whatever values you take, you will get a particular value of n square, and that will give you a particular energy. Like if you're taking nx 1 to 1, or 2 1 1, or 1 1 2, or you can take 1 1 2. So these correspond to the same energy. So this correspond to the same energy. So this will give you degenerate states. These are basically degenerate states which correspond to the same energy. So you can basically plot a graph and you can show the degeneracy. Okay. Okay, I think this is clear a little bit. You got an idea. I'm not doing everything. It will take time. So basically n square is nx square, ny square, nz square. Linear combination we are taking. And this, what are the values of, what are the possible values of nx, ny, nz, so that you will get a particular value of n square that correspond to some energy, and that is called degeneracy. Okay, we can go for another example. Let's say oscillator. We can go for another example. Let's say oscillator, quantum oscillator. I think you got some idea about the degeneracy. The energy is basically n squared pi square h squared square divided by 2m square. These are the constant factor. This n square is what? Nx square, ny square, z square combination. So what are the possible values of nx, ny, nz? So you can take 1 1 2, 1 2 1, 2 1 1. So these values of nx, ny, nz, they correspond to the same energy. Are you getting my point? If you take nx first value 1, ny equal to 1, and z equal to 1, that correspond to the 0 point energy. Now what are the possible values you can take? You can take nx equal to 1, let's say, ny equal to, let's say, 2. You cannot take 0. Okay, that is very important. Ny equal to 2 and nz equal to, let's say, 1. This is one combination you can take. Or you can take nx equal to 2, this is 1 1, or this is 1 1 2, you can take. So all these values of nx, ny, nz correspond to the same energy, and that is called what? Degeneracy or degenerate states. Okay, and basically we can take another example. Let's say in case of harmonic oscillator. If you take harmonic oscillator, that is like a spring. If you think of a spring, that is a harmonic oscillator, and we can plot the energy eigenvalue. Let's say I'm talking about I'm writing the formula only. If you talk about the three-dimensional harmonic oscillator, then the energy eigenvalues are basically n plus 3 by 2 h cot omega. So this n is what? N is basically nx, ny, and nz. These are the values of nx, ny, nz. Okay. So here is basically you can take nx, ny, nz as 0, because if you take also you will not get 0 energy, and that will give you this is not giving you 0. If you take capital M0 also, then the energy is 3 by 2 h cot omega. That is not 0. That is the minimum energy. So that combination you have to keep in your mind. This nx plus ny plus nz equal to what? Capital N. Okay. This capital N correspond to the numbers, quantum numbers. So basically this nx, ny, nz, what are the values of nx? What is the value of ny? What are the values of nz? This nx can go from 0 to like any number. This can go from 0 to any number. This can go from 0 to any number. So since nx, ny, nz are equal to n, like nx square plus ny square plus nz square we are taking, and this basically this nx, ny, nz are basically what correspond to the values of what n. So this basically you can take 0, but in that case you cannot take 0 nx, ny, nz. Remember the point. Okay. So since this n you can take 0, you can take 1, so you can take any number. Then basically in that particular case 0 was not allowed, because the total energy will become 0. That n square was there. Are you getting what? Nx square plus ny square plus nz square, and nx, ny, nz. This is the minimum energy, and you can go from other possible values of nx, ny, nz to get the same energy or degeneracy. So here this n can go from 0 to any number. Okay. Let's say if you take n equal to 0, that is the ground state. That is basically the ground state. How many quantum state it will have? So you can check it. Basically, you can check it. For the ground state, if you take n equal to 0, then you will get what? E0 is equal to 3 by 2 h cot omega. That means what are the possible values of nx, ny, nz? Nx, ny, nz, they give 0. So only one possible quantum state. Only one possible. This nx, ny, nz are the quantum state. So this is only one possible quantum state. Now if you take what? N equal to how much? Let's say n equal to 1. So what are the possible values of nx, ny, nz, so that you will get this n equal to 1? This nx can be 1, ny can be 0, nz can be 0. This is one possible value. Or you can take nx equal to 0, ny equal to 0, nz equal to 1. This is one possible value. Or you can take nx equal to let's say 0, ny equal to 1, and nz equal to 0. This is one possible value, and all these correspond to the same energy only. Okay, all these correspond to the same energy only. So for n equal to 1, that is the first excited state, you have how many quantum state? This basically you have 3 quantum state, nx, ny, nz, 1 1 1 0 0 0 1 0 0 1 and 0 1 0, like that you can take. So basically for n equal to 1, you have 3 quantum state. This is basically 1 0 0 one quantum state. This is another quantum state, that is 0 0 1, and this is basically another quantum state 0 1 0. Okay, these are my quantum states. You can imagine a little bit. This is my quantum state. Okay. Okay. So you can basically plot this. These are my quantum state: 1 0 0 0 1 0 and 0 1 0 0 0 1. This is my, so this is basically this corresponds to the same energy. Energy is how much? If you put 1, it is basically 5 by 2 h cot omega. So this is basically threefold degeneracy. How much? Threefold degeneracy. Okay. Now you can move for the higher numbers. Like for the lower, it is E0 is basically how much? 3 by 2 h cot omega. And this corresponds to a single quantum state. 0 0 0. This is 1. Okay, and each quantum state is assigned with a wave function, because wave function is used to find the observable, and quantum state basically gives the observable only, because here the quantum state basically depict the energy. If you see this quantum state, this give a energy, this also give the same energy, this also give the same energy. So using wave function we can find the energy. Using the wave function, that is psi, we can find the observables, and quantum states are nothing but observable. That means energy. So using the wave function we can find the energy, or we can find the observable, and quantum states are basically observed. So using wave function we can find the quantum state of the particle. So for which we can say that each quantum state is assigned with some wave function psi. Okay, so this is my diagram I can show. If you go to the higher state, let's say second excited state, you will get six-fold degeneracy. You can do basically. This is actually very good practice. You can do n equal to 2. If you take n equal to 2, you will get energy how much? Energy is basically E2, that is 2 plus 3 by 2, that is 2 to 4 plus 3, 7 by 2, h per omega. So what are the possible values of nx and by nz to get 2? You can do it. Okay, 2 0 0. You can take 1 1 0, or like that you can take 1 1 0 1 0 1 0 1 1 2 0 0 0 2 0 0 0 2. This gives the corresponding energy 7 by 2 h naught omega. So this is the six-fold degeneracy. So second excited state corresponds to six-fold degeneracy having same energy. Three-fold degeneracy, six-fold degeneracy. Then you will go to the next excited state, you will get tenfold degeneracy. And this harmonic oscillator is only applicable for hydrogen atoms or hydrogen-like atoms, because whatever we are talking about hydrogen atom or hydrogen, this is one quantum state, and basically we call this as S-state, spherical symmetric, you can say spherical symmetric, because in this particular state, if you consider a hydrogen atom, the ground state of hydrogen atom, then the electron will occupy the S state. You have different quantum state, or different shape of orbitals, like S, P, D, F, like that you can have. Okay, when you go to the excited state, then electron will be in the P state. Electron will be in the P state. Electron will be in the P state. In S state, if you take the electron, is basically the electron is in the S state in the case of hydrogen atom, ground state of hydrogen atom. If electron is excited somehow, it is excited, it will go to the P state. So threefold degeneracy means it is P state basically, and in P state we are having different rooms, and electron can be in any room. Okay, so for the next excited state, are you getting my point? For a ground state we have different orbitals, but for ground state electron is in only a state, that is the spherical symmetric of the system. That's why we deal with the spherical harmonics. Spherical harmonics is basically the shape of the orbitals. Shape of the orbitals means that is only for the ground state of hydrogen atom or hydrogen like atom. Let's say helium plus, like that. Okay, so in that particular ground state of the hydrogen atom, we are having spherical symmetric. Spherical symmetric means S state. Then we will have P state. P state is like dumbbell shape, then double dumbbell. These are the structure you will get. Okay, shape of the quantum state. So here the shape of the quantum state is what? Spherical. S state means spherical shape, and here it is the P state, the excited state. P state. So P state means what are the shape? What is the shape of this quantum state? So you can find the shape of this quantum state. That is like dumbbell, double dumbbell, like that. Dumbbell or double dumbbell, like that. So this is like yes. Okay. So this ground state is corresponding ground state means this is my quantum state. Okay, this quantum state. So this particular quantum state, I can find the shape of this quantum state, and this corresponds to the S state. S state means spherical symmetric. The spherical symmetric of the system. So one can basically study the spherical symmetry of the system, or analyze the spherical symmetry of the system. Yes, by considering the wave function in the spherical polar coordinate system. Okay, then we can study, but this is not our topic of discussion. we are basically interested to know the quantum state. Okay, so if you consider this as the energy E, and this is basically, let's say, a little bit higher energy, let's say E plus dE. So how many quantum states are there within this range of energy? That is within E to E plus D, 1, 2, 3, 4. So there are 4 quantum states. There are 4 quantum states. And these are basically called density of states. So what is density of states? Density of states is defined as the number of quantum states that is available per volume per unit energy interval. Per unit energy interval, that is dE. Per unit energy interval is basically dE. So that means within this energy range, E to E plus dE, how many states are there? That is the quantum state. The unit of the density of states is basically, I can clear this diagram. Can I? May I? Okay. Okay. I'm clearing all the diagrams. Okay, 1 minute. Okay. So what is the definition of density of states? Now one can write the definition. The definition is basically what? The number of density of states is defined as the number of quantum state per unit volume. Okay, per unit energy interval, unit energy interval TE. Okay, you can find the unit. Actually, unit is basically what? Number of quantum states divided by what? Volume per energy, per energy. So per unit volume means divided by volume. Let's say centimeter cube per unit volume, or meter cube, anything like that. Okay, per unit volume, per unit energy, number of constant per volume per energy. So you can take the electron volt, isn't it? So this is the unit. Unit is basically what? 1 by, unit is basically what? It will come in basically centimeter power minus 3 electron volt minus 1. Okay, so this is basically, you can find the unit. One can basically write in this form, write this definition, or write the unit of the density of state. So density of states, I will repeat this: the number of quantum states that is available per unit volume, per unit energy interval dE, per unit energy interval dE. So number of quantum states which is available per unit volume per unit energy interval dE. That means what? Are you getting my point? It is the number of quantum states that is available per unit volume, like density is divided by per volume, per unit volume, and per unit energy interval dE. Per unit energy interval dE means within the energy range we are finding. Within the energy range, that is E to E plus dE, we are finding the total number of what? Quantum states which is available. Okay, if one basically, now we have the states. Okay, now we have the states. Now the question is, how these states are occupied? How these states are occupied? That is given by the occupation probability. Occupation probability gives how these states are occupied. Suppose, let's say the occupation probability is 1, or occupation probability is basically half. Anything you can find, half or 1, anything. That means all these states will be occupied. Probability is 1 means all these states will be occupied. This state, this state, this state, this state, all these states are going to occupy. If the probability is half, then 50% chance is that it will be occupied, 50% chance is that it remains empty. Let's say it is occupied, let's say it remains empty, let's say it is occupied, let's say. So one can basically find how these states are going to occupy. These are the states, these are the possible states which is available for energy interval, that is number of quantum states available within the energy range, what? E to E plus dE, and that we define as the number of quantum states available per volume per energy interval dE, per unit energy interval dE. That means how many states are there within the energy range into E plus dE, and how these states are occupied. How these states are occupied. States are occupied. That is given by occupation probability. Occupation probability F of E. F of E. That we have done 1 by e to the power E minus EF by kBT plus 1. Okay, that we have done. That is not a big stuff or not a difficult stuff for us, okay, to understand. But we will understand this, how these states are occupied. That is given by occupation probability, and we will take the different temperature. Let's say T equal to 0 Kelvin, T above 0 Kelvin. That we will take, and we will decide the occupation probability. For T equal to 0 Kelvin, the occupation probability remains 1 or 100%. For T greater than 0 Kelvin, the occupation probability became half. And in that case, we are going to define the Fermi level. Okay. So if one knows the density of the states, that is how density of states is represented. That is basically G of E dE. G of E dE means what? Why it is represented by G of E dE. That means the number of states available within the energy range, E to what? E plus dE. Then we are taking number of quantum states which is available per volume per unit energy interval dE. That means within this energy range E to E plus dE, how many states are available? That we have to take. And this is basically we are taking this per energy interval dE. That is E to E plus dE, and the difference you can find. The difference is basically what? E plus dE minus E. That is dE only. Okay. So the number of quantum states available within the energy range E to E plus dE. That is the per unit volume per energy interval, per unit energy interval. That's why it is E to E plus dE. E dE means within this energy range, how many states are there? That is called density of cells. So G of E dE. So if you want to find the electron concentration, one want to find the electron concentration. Suppose the probability is half. That means let's say this state is occupied. This state remains empty. This state is occupied. This state remain, let's say 1, 2, 3, 4. Okay, we have 4 states. Okay, this state remain empty. So one can find the electron. That means N of E dE. That means the particle concentration within the energy range E to E plus dE. How much it can be? If you multiply the density of state with this occupation probability, you can generally find G of E dE multiplied with F of E. If you multiply this, 4 quantum state multiplied with half, so the number of particles is 2. So how many particles will be there? 2. So you can see we have 2 particles. Okay. So this we are going to do. This is one example, but we are going to deal this system. Okay. We are going to deal the system by considering the practical idea. Practical idea means we don't know how many particles are there. We don't know how many states are there. For in this particular case, we can count 1, 2, 3, 4. But practically, we cannot count how many states are there. So we need a general formula. We will derive that formula for density of states, because practically we don't know how many quantum states are there. Practically, we don't know how many electrons or how many particles, because in this case, electrons, fermions is the only case we are discussing. So how many electrons are there? We don't know. So we will find the electron concentration. In next class, we will find a general expression for the density of the states, because we don't know practically how much states are there, and we will see the occupation probability at different temperature, and then we will find the electron concentration, and we will try to relate this electron concentration with the Fermi energy. So that this class was all about the idea about the stat mech, or idea about this Fermi gas. Fermi gas means electron gas, and already we have discussed classical statistics, quantum statistics, and what? Macro micro. So thank you. I will stop this recording. If there is any doubt, you can ask.